Good day, everyone! This episode is for grade 12 students who are studying physical science. But of course, everyone who is willing and interested to learn is welcome to join us. Make sure that you have a pen and paper with you so you can write the things that you will learn from this episode. I am Teacher Iman and I welcome you to the second episode of Science Eskwela TV, where you can learn science concepts in fun and easy way. In our previous episode, we learned how the light elements were made during the Big Bang nucleosynthesis and how hydrogen atoms fuse to form helium inside the stars. In this episode, we will discover how heavier elements are formed inside the stars, and let's watch this documentary about the stars and learn more about what goes on inside these hot balls of plasma. All living things require energy. Not only to engage in activities like walking, running, or swimming, but also to survive. Without energy, we will not be able to do simple things like eating, talking, or even breathing. Our body needs energy to keep going. Our heart needs energy to pump blood throughout the body. And our lungs need energy to breathe. Thanks to the sun, we can get the energy we need to do these things. I am Correspondent Sunny, and this is my report. Plants use sunlight to make carbohydrates, which becomes our main source of energy. And where does the sunlight come from? Of course, from the nearest star in our planet, the sun. Our sun is just one of the billions of stars in the Milky Way galaxy, and one of the billions of trillions of stars in the universe. They come in different sizes and colors. All of them release energy. Each of them fuse elements at the core to form new ones. How were the stars born? Where do the light and energy they release come from? Do stars explode? What happens to them when they do? We have asked the Manila Street astronomers to help us find answers to these questions.
One of the more common questions asked about stars is, how are the stars born? Well, a star is born inside a huge gas cloud made up mostly of hydrogen, helium, dust particles, and called a stellar nebula. These gas and dust particles begin to clump together due to the force of gravity, and these clumps merge together to form bigger clumps. Okay? The force of gravity increases the kinetic energy of the dust and gas particles. This increases the temperature of the nebula. The temperature and pressure become so great that the hydrogen atom starts to fuse. This fusion of hydrogen atoms release a lot of energy and light, giving birth to a star.
Stars are able to brighten the night sky because of the energy they release. The star's core is where most of its energy is produced. Hydrogen atoms fuse together to form helium, which releases a lot of energy in the process. This process is called nuclear fusion.
The powerhouse of a star is the core. The energy released from the nuclear fusion provides the outward pressure that counters the inward gravitational force of a star. Without this outward pressure, the star will collapse.
Our sun will continue to fuse hydrogen for the next 5 billion years. What happens after that? What happens when it runs out of hydrogen in its core?
So once a star runs out of hydrogen, it can no longer hold against gravity. Its inner layer will start to collapse due to gravity, and the core shrinks. So as the star collapses, the temperature and the pressure at the core increases. Eventually, the core becomes hot enough for helium atoms to fuse and form new or heavier elements. At this stage, the star expands bigger and forms either a red giant or a supergiant.
The fate of a star depends on its size. An average-sized star will become a red giant, while a massive-sized star will become a supergiant star. Red giants are capable of fusing helium atoms to produce carbon and oxygen. Supergiant stars can fuse elements heavier than carbon up until iron. When a red giant runs out of helium to fuse, the outer layers are ejected. Eventually, its core will be exposed. Though dead, the core will remain hot for billions of years. It is called a white dwarf. Red supergiants do not die as quietly. When it dies, it collapses, and then it explodes. The explosion is so big that it releases a huge amount of energy. For days and even for weeks, it can outshine the whole galaxy.
Now, a supernova happens when a supergiant can no longer release energy from fusion. The outward pressure produces from its core eventually decreases until it can no longer withstand the inner force of gravity. This causes the star to collapse to a smaller and denser core. It produces an enormous shockwave that causes the explosion. The explosion also spreads the newly formed elements throughout outer space. They can become building blocks for future planets and other stars. The supernova will then leave behind either a neutron star or a black hole. The energy released by the supernova makes it possible for the elements heavier than iron to be formed.
Aside from supernova, elements heavier than iron can also be formed from collision of two neutron stars. It is truly beautiful to behold how stars brighten the night sky, but it is more amazing to realize that the oxygen that we breathe, the calcium in our bones, the iron in our blood were made inside these stars. As to the process of how these elements were made, I'll let Professor Proton teach you that.
Hello everyone and welcome to my classroom. I am Professor Proton and I will be discussing a different process by which heavier elements are made. On the previous episode, my friend Professor Atom taught you how helium is formed through the proton-proton chain reaction. That process is more dominant in medium-sized stars, just like the Sun. But for bigger stars, the more dominant process in fusing hydrogen to form helium is called the CNO cycle or the carbon-nitrogen-oxygen cycle. The process starts when a hydrogen atom or a proton collides and combines with carbon-12 atom. If you look at the periodic table of elements, you will see that carbon has an atomic number of 6. This means that it has 6 protons. Why then do we call it carbon-12? The number 12 here represents the mass number or the total number of protons and neutrons. This means that carbon-12 has 6 protons and 6 neutrons. When hydrogen atom hits carbon-12, 1 proton is added to the nucleus. Now it has 7 protons and 6 neutrons. We learned in our last episode that the identity of an element depends on how many protons it has. Now that the number of protons in the nucleus has changed, its identity has also changed. As you can see, it has turned into nitrogen-13. Instead of 6, the nucleus now has 7 protons. This nitrogen-13 is not stable. It will eventually turn into carbon-13. How did that happen? One of the protons in nitrogen-13 turns into a neutron. This changes the total number of protons into 6 and the total number of neutrons into 7. 6 protons and 7 neutrons. Later, another hydrogen atom will hit carbon-13. The total number of protons will change again. As you can see from carbon-13, the nucleus turned into nitrogen-14. Because instead of having 6 protons and 7 neutrons, we now have 7 protons and 7 neutrons. Then another hydrogen atom collides and combines with the nucleus. This results to the formation of oxygen-15. The change was caused by the addition of proton in the nucleus. Now, the nucleus has 8 protons and 7 neutrons. What we have left is another unstable nucleus. One of the protons in oxygen-15 turns into a neutron. Since the number of protons changes, the identity of the element changes. It will become nitrogen-15 atom. And nitrogen-15 has 7 protons and 8 neutrons. 7 protons and 8 neutrons. Lastly, the 4th hydrogen atom hits nitrogen-15. Now we have a total of 8 protons and 8 neutrons. However, 2 protons and 2 neutrons are released. That is helium. Now what is left is another carbon-12 atom that has 6 protons and 6 neutrons. If another hydrogen atom hits carbon-12, then another cycle occurs. As you can see, 4 hydrogen atoms were used in the process. 1, 2, 3, 4. And this is how helium is formed through the CNO cycle.
Thank you, Professor Proton. The CNO cycle will only work as long as there is hydrogen to keep the cycle going. Earlier, we learned what happens when the stars no longer fuse hydrogen at their core. Medium-sized stars turn into red giants, and massive stars turn into supergiants. Inside these dying stars, elements heavier than helium are being fused. My friend Professor Electron will show you what happens inside their cores. Hi, this is Professor Electron, and I'm here to show you the processes at which elements heavier than helium are made. But first, we need to go inside the core of a dying star. When a star turns into a red giant, the core is filled with helium atoms that are fusing together to form new elements. 3 nuclei of helium collide and combine together to form carbon through the process called triple alpha process. The process starts with 2 helium nuclei colliding and combining together to form beryllium. This beryllium is highly unstable and it could decay back into a smaller atom. However, if another helium atom collides and combines with it before it decays, carbon is formed. This process releases energy, and because of that, some carbon nuclei fuse with additional helium and forms oxygen. Notice that 3 helium nuclei were fused to form carbon. Helium nuclei is also known as alpha particle. That is why the process is called triple alpha process. Now let's take a look at how the alpha ladder process occurs. Another type of nuclear fusion process that combines helium to form heavier elements is the alpha ladder process. The basic concept is the same. Atomic nuclei collide and combine to form heavier ones. And since this is an alpha process, helium nuclei are always involved in the said reaction. For example, carbon combines with helium to form oxygen, and then oxygen fuses with helium to form neon. Then neon combines with another helium to form magnesium, and so on and so forth. Triple alpha process and alpha ladder process fuse helium nuclei. Heavier elements can also be formed through the fusion of other heavy elements. For example, 2 carbon nuclei can fuse to form magnesium. This is called carbon burning. Another example is when 2 oxygen nuclei combines to form silicon. This is oxygen burning. Now, if we want to understand how elements heavier than iron are formed, we'd have to talk about a different process, and that process is neutron capture. It is very difficult to make heavy elements by fusing them together. It requires a very large amount of energy. This is because the heavier the element gets, the more protons it has, and when you bring protons closer to one another, they repel each other because they have the same charge. That is where neutrons come into play. Unlike protons and electrons, neutrons have no charge. It is easier for them to approach an atom and get absorbed by it. That's the basic concept of neutron capture. You have a seed nucleus like carbon or iron, and then you bombard it with neutrons and they get absorbed in the nucleus. This will increase the mass of the nucleus, but you have to remember, it will not change its identity. If the seed nucleus is iron, the addition of more neutrons does not change its identity. However, some of these neutrons will eventually turn into protons, and when that happens, you'll have elements that have an atomic number higher than iron. There are two types of neutron capture, the S process and the R process. The S stands for slow and the R stands for rapid. Slow and rapid refers to how fast the neutron bombardment occurs. Let's discuss the rapid neutron capture process. In this process, the seed is bombarded with huge number of neutrons in about 1 to 2 second time scale. For this to occur, there must be a lot of neutrons and there must be a lot of energy. Scientists believe that the R process occurs in supernovae or star explosions and in neutron-star mergers or the collision of two neutron stars. As shown earlier, the neutrons that were captured by the seed nucleus will eventually turn into protons. The slow neutron capture process occurs in less energetic environment than supernova and neutron star mergers. It takes place inside the dying stars. Unlike the R process, the bombardment of seed nucleus with neutrons takes a long time. It can take thousands of years. How does this process work? We know from the earlier discussion that for neutron capture to occur, the environment must be rich in neutrons. Apparently, the alpha processes produce a lot of free neutrons. These neutrons are captured by the seed nucleus, but it takes a longer time to happen. That's how the heavier elements are made through nuclear fusion and neutron capture. Oh, I have to go. I still have to do some combination of protons and neutrons. See you! Wow! Did you have fun learning about the processes that form the elements? I'm sure you did. Let's review them. We have already answered one of the most interesting questions in science. How were the elements formed? All elements originally formed from hydrogen, which was formed during the Big Bang nucleosynthesis. A few moments after the Big Bang, protons and neutrons collided and combined to form helium and some lithium and beryllium. Elements also formed inside the stars in a process called stellar nucleosynthesis. Hydrogen atoms fuse to form helium through the proton-proton chain reaction and CNO cycle. Proton-proton chain reaction is dominant in medium-sized stars like the Sun, and CNO cycle is dominant in high-mass stars. Elements heavier than helium are formed from further collision and combination. When three alpha particles or three helium nuclei collide and combine to form carbon, the process is called triple alpha process. Helium nuclei can further fuse with elements like oxygen, neon, magnesium, silicon, etc. in a process called alpha ladder process. Elements heavier than iron are formed through the process of neutron capture, where a seed nucleus is bombarded with neutrons, which makes the elements unstable. A fraction of the neutrons will then turn into protons to make a more stable element. There are two types of neutron capture process, the R process and the S process. The R process, or rapid neutron capture process, occurs in supernovae and neutron star mergers. The S process, or slow neutron capture process, occurs in dying stars. Now it's time to check how much you understood from the episode. All you have to do is to choose the letter of the best answer. Let's start with an easy question. Question number 1. What is the explosion of the stars called? A. Supernova. B. Black hole. C. Neutron star. Or D. Big Bang. The correct answer is A. Supernova. Question number 2. Which of the following gases are the major components of a main sequence star? A. Carbon and oxygen. B. Helium and carbon. C. Hydrogen and carbon. Or D. Hydrogen and helium. The answer is D. Hydrogen and helium. Question number 3. What object is formed from gas and dust particles which are pulled together by gravity and no nuclear fusion has happened yet? A. Nebula. B. Main sequence star. C. Red giant. Or D. Red supergiant. The correct answer is A. Nebula. Question number 4. Which of the following refers to the process at which 3 helium nuclei are converted into carbon? A. CNO cycle. B. Neutron capture. C. Supernova nucleosynthesis. Or D. Triple alpha process. If you answered D, then you are correct. Triple alpha process. Question number 5. Which of the following processes takes place in supernovae and neutron star mergers? A. CNO cycle. B. Rapid process neutron capture. C. Slow process neutron capture. Or D. Triple alpha process. The answer is B. Rapid process neutron capture. How did you do? Did you find the questions easy to answer? I hope you did. Before we end this episode, I'd like to share something that I hope will encourage you. You might be thinking why it is important for you to learn the processes we discussed in this episode. How are you going to use them in your future job or endeavors? It is highly likely that you will not, unless you work as a scientist or teacher like me. Then why are we teaching this? No matter what type of job you will have in the future, you will be required to learn processes and how things are done. By learning about these things, you are training your mind to be better at remembering processes, improve your ability to see the connections between step 1 and step 2, and easily interpret illustrations that show processes, like illustration that shows the process of CNO cycle, or a very useful illustration that shows how CPR is done. And that's it for this episode of Science Escuela TV. On our next topic, we will talk about how the elements are synthesized inside a laboratory. Don't forget to tune in on our next episode because learning science with Teacher Iman is fun!